Applying components. When working with vectors, such as in a navigation or applied force problem, it may be useful to separate the initial vectors into components. Okay, as I go through the examples here, this is going to be a little bit of a building process. Example 1 is really going to be about how to separate into components. After that, we can start to look at how we can use the components to figure out the resultant vector of an applied problem. All right, for example number 1, an airplane travels at a course of 50 degrees at 600 knots. Okay, let's go ahead and start with a simple picture of that. Okay, I'm going to let this be a compass. We have a north direction. Okay, 50 degrees is going to be measured off of the north, which is going to place the vector not directly in the middle of that quadrant, but a little bit in the southern direction of that. Okay, let's use a different color for the vector. All right, now the length of this is arbitrary. You can choose it to be whatever you want, but it is going to represent 600 knots. Okay, that would be nautical miles. The angle that we have is 50 degrees, which means that the angle here is going to be 40 degrees, which will be reported in just a moment. What we want to do here is figure out the northern and eastern speeds. That would be the components of this vector. Okay, to do that, what I'm going to do is first extend that out just so I have a nice horizontal, and then I'm going to build a right triangle. Okay, so that this vector here is going to represent that northern speed. This vector is going to represent that eastern speed that you'd have here. Okay, so in a sense, what we're trying to figure out is what would be the y component, what would be the x component. And you may remember that we basically did this stuff with polar coordinates. To get the x component in this situation, what we would do is take the radius length, which is 600 knots, and multiply that by the cosine of the angle that we have here. Okay, and it ends up being as simple as that. That is how you can get the horizontal component out of that vector. Okay, for the y component, pretty much the same thing. You're going to take the 600, which would be the radius length, or in this case, the magnitude of the vector, multiply that by the sine of 40. All right, so let's see what those turn out to be. We'll go ahead and just write this up first. Okay, for the x, let's see if I can do this without covering it. Well, I'll just type it in. All right, for the x, we're going to be looking at 600 times the cosine of 40. Okay, 600 times cosine 40, which is going to give us approximately 459.6 knots. Okay, and then for the y, the only difference is you change it to sine, which is going to give us 385.7. We'll go ahead and add on here knots. All right, one more thing that we can do here just to verify that this is actually true. We could do Pythagorean Theorem. We could do x squared plus y squared and show that it'd be the same thing as the 600 squared that we have there. Now, of course, if I use these numbers, they would be rounded off answers, so you're not going to get exactly that value. So I'm going to type it in using these that I have. Okay, so I'm going to open up parentheses, 600 cosine 40. We're going to close and then close so that we can square it all together. Make sure I double count all my parentheses. Okay, so that's like your x squared. Then this will be our y squared. Close, close. That. All right, and we get exactly 360,000, which is the same thing as 600 squared. All right, for example number 2, what we're going to do is use the component forms of two vectors to figure out the resultant vector. Okay, for our problem, we have a ship that sails 3 miles on a course of 40 degrees. That would be in a more northeastern direction. After that, it's going to travel 8 miles on a course of 100 degrees, which is going to be mostly in east direction, but with a little bit of a south to that as well. So overall, our picture is going to be moving mostly to the right. Okay, we'll go ahead and do a quick sketch here, and we'll try and get it scaled out somewhat nicely. All right, 3 miles at 40 degrees. Okay, so 40 degrees is going to be a little bit more the north direction with this. I should probably do these in centimeters if I want to keep it scaled nice. Okay, so we'll say that that's 3. At the end of that, all right, I should probably add in one more thing, which is that is 40 degrees. Okay, so then after that, it's going to be at 100 degrees, 8 miles. Okay, so it's going to be a little bit below east, because east would be at 90. Okay, so we're about there. Let's put a little dot at the end just for something. And 100 degrees, which is going to make that 10 degrees. There's some other values you could probably throw in there if you want. That would be 80 degrees. Okay, so depending on the approach that we take with the problem, today is going to be component form. You could potentially use the 80 degrees right there. You could use alternate interior angles to do the 40 degrees there if you're going to build like a full triangle. Of course, our approach here is going to be a little bit different, which is using component form. Okay, so for the first vector that we have here, to get the components, okay, we got an x and we got a y component. The x component, which I would visualize here, is going to be the magnitude 3 multiplied by the cosine of this angle that we'd have there, which is 50 degrees. Okay, so we were given the 40. I'm going to go ahead and take that out of the picture though. Okay, you're given the 40, but if I'm imagining the right triangle like I did in example 1, this would be the angle that we want. Okay, so the x component is going to be 3 cosine 50. All right, then the y component, if you've got that one, it's pretty straightforward. The vertical to this is going to be 3 sine 50. You get that. Okay, for our second vector, for the x component here, you can actually visualize it on the top side if you want. Okay, so you'd have the x direction, you could then have the y direction. The picture would be upside down compared to the other one, but the 10 degrees would still be adjacent to that x direction, which would allow us to take the magnitude, which was 8, multiply that by the cosine of 10 degrees. Okay, and then the vertical, which would be over here, would be 8 sine 10. So that distance right here is still the opposite side from the 10 degrees. All right, so how do we use these to figure out the resultant? Simply put, what we can do is just add the x's together to get an overall x distance. We can also add the y's together to get an overall y direction as well. All right, so for the x's, we're going to take 3 cosine 50 and add that to 8 cosine 10, which is going to give us 9.81. Okay, so for our x component of the resultant, it's approximately 9.81. Okay, now for the y component, this is actually going to be a little bit different because if you pay close attention to the values and how I described in the picture, this is going up, but that is actually going down. So you don't really want to add these two. You are going to have to subtract them because they do move in different directions here. Okay, so I'm going to take 3 sine 50 and subtract, let's close that parentheses, subtract 8 sine 10, which is going to give us a positive number here, which means it is mostly moving up, which is what it looks like in our picture, just barely though. Okay, so we're going to get let's call it 0.91. That's what we'll get there. All right, so those will be the components of the resultant, which means that if we did Pythagorean theorem with those numbers, we could figure out the distance from here to there, which is ultimately what the question wants. How far is the ship from its starting point? Now, to be as exact as possible, because these are rounded off answers, what I can do is just highlight these, square them, okay, add them together. You get that answer, which is pretty convenient here. You get exactly 97, so we could take the square root of 97, which is going to give us 9.84. All right, for example 3, we're going to do a little bit of a physics problem. This, as far as a diagram, can get a little bit confusing, but once you do a few of the problems, you really will get used to the idea and how you build these. Okay, so the situation that we have is that a 2,000-pound car is parked on a street that makes an angle of 12 degrees with the horizontal. So we have a car that is on a slope. okay, at a 12-degree slope. And of course, if that car were put in neutral, it would roll down that hill. Okay, so our question here is to find the magnitude of force required to keep the car from rolling down the hill. In other words, some outside force, such as maybe a parking brake, would need to apply enough pressure to keep the car from rolling down the hill. In addition to that, we are also going to find the force that would be perpendicular to the street. That is a little bit more of a physics-based thing that in our problem, we might not understand why that applies, but it would be one of our components, so we might as well go ahead and solve for that. So this all begins with the 2,000-pound force, which is going to be directed straight into the earth, regardless of the slope that it's going to be sitting on. So that force, we can draw it here. I'll just start from the center of the car and make a vector in that direction, and that's going to be 2,000 pounds. Okay, that's going to be 2,000 pounds. Now, it does have two components to go with it. One of them is going to be the one that moves the car down the hill. The other is going to be perpendicular to it, which means it's perpendicular to the road that you'd have there. Okay, so what I'm going to do, this is a little bit odd, but you got to look at it somewhat as an angle and think this is a hypotenuse. Okay, I'm going to draw what would be a perpendicular to that road. Okay, I'm going to do that until I have it lined up with my vector, at which point what I'll do here, let's actually make these just a little bit shorter. They don't have to be that long. All right, so then I'm going to make a perpendicular here. Your components are always going to be perpendicular with each other. Okay, so the first question is really going to be about this vector here, because that will be the one that runs parallel to the hill. The other one is the perpendicular to the street one. Okay, so in a way, what you're going to notice by looking at the diagram is that most of the weight that we have here is actually going to get absorbed by the road, and just a little bit of it is going to be used to push the car down that hill. All right, so we do have a right triangle, okay, but we need to figure out how to get that angle measurement into this picture. Okay, now there's a couple different ways you can do this geometrically, but for this, I usually just rely on a simple rule, which is the angle that you have here, the 12 degrees, will also be the angle that you get there. Okay, so there's some geometric ways you can actually prove that that is true, but it always will be. So I'm going to go ahead and just pass that information on to you, that this angle will be that angle there. All right, so to figure out the components, let's go ahead and call this the y component. Let's call that the x, just because it sort of looks like that in my picture right now. Okay, the y component is going to be equal to the magnitude, 2,000, multiplied by, okay, and if we're going to use the 12 degrees here, that would give us actually a cosine in this case. So it's a little bit weird, right? Because that, which I just called here the y, is actually adjacent to the 12. So that's going to be a cosine 12. Okay, and then what I called the x over here is going to be 2,000 times the sine of 12 degrees. All right, so there's a little bit of conflict in how I chose my letters, right? I chose this to be x, chose that to be y. Y is typically going to be associated with sine, but because of the way that I drew the picture, this side right here is adjacent to the 12, so you need to use cosine. This is opposite to the 12, so we're going to use sine. Let's go ahead and type this in here. We'll go ahead and start with this one. 2,000 times the sine of 12 is going to give you 415.8. And that is going to answer the first question. Let me go ahead and just put a little letter A there, just so we keep them organized. So that's going to be A. This is going to be question B that we have here. So A, the force that the car would be rolling down is going to be 415.8 pounds. Okay, that would mean that if you wanted it to not roll down, the parking brake would need to apply 415.8 pounds in that direction to keep it from moving. All right, your B, that is going to be a bigger value here. We're going to get 2,000 times the cosine of 12, significantly bigger. You get 1,956 or 1,956.3 pounds. All right, so the majority of the 2,000 pounds is actually being absorbed by the road over here with the 1,956. And just 415 pounds is being applied to move the car down the hill.
Later, blah.